The most dangerous places on Earth look completely normal, and so does the data. Clean charts, tidy averages, official reports filed on time. But underneath all that order, there are 13 places across the United States where the numbers refuse to behave, where temperatures swing in ways no model predicted, where rain arrives when it should not, and vanishes when it must, where snow falls in the desert, and heat waves kill livestock in regions that should be cold. Scientists have names for most of these. They have theories for all of them, but explanations that fully satisfy the evidence, that's a different story. Today we'll walk into Death Valley, where the rocks move across a dry lakebed without a single witness. We'll stand inside a forest in Washington state, where annual rainfall measurements have contradicted every climate model for 4 consecutive decades. And finally, we'll enter a region of the Gulf Coast, where sea surface temperatures reached levels in 2023 that no instrument in recorded history had ever measured. Levels that shouldn't exist at all. Deep breath. Let's go. 13. Welcome to the moving stone floor. The racetrack playa in Death Valley National Park is one of the most photographed geological puzzles in the American West. It sits at an elevation of 3,608 feet in the northern part of Death Valley, a perfectly flat expanse of cracked, pale mud, roughly 2 miles long and 1 mile wide. And across its surface, rocks move. Not quickly, not visibly, but over months and seasons, stones weighing hundreds of pounds leave trails, long, shallow grooves pressed into the dried clay, sometimes perfectly straight, sometimes curving in arcs, sometimes making near right-angle turns. Some trails run parallel, some cross. Some stones have traveled more than 1,500 feet from where they started. The unofficial explanation from the National Park Service matched what common sense suggested for decades: wind. Strong desert wind pushes the rocks when the playa surface is wet. But here's where the anomaly lives. Weather records for the racetrack show events where rocks moved during periods when sustained wind speeds in the surrounding valley were not strong enough to shift a stone of that size across a surface of that friction. The math doesn't fully close. In 2014, researchers from the Scripps Institution of Oceanography placed GPS sensors on rocks and recorded what actually happens. A thin layer of ice forms overnight. The ice sheet breaks into panels in the morning sun, and light wind, sometimes as low as 10 miles per hour, pushes the ice panels across the slick playa surface. The panels drag the rocks along for minutes at a time. It's elegant. But the formation of that precise ice layer, at that precise depth, in a desert that regularly sees temperatures above 120 degrees Fahrenheit in summer, depends on a confluence of atmospheric conditions that no regional climate model reliably predicts. The National Weather Service station nearest to the racetrack is more than 50 miles away. The microclimate inside that playa basin operates almost independently of the surrounding desert. Temperature records from sensors left inside the playa for multi-year periods show variance patterns that still generate disagreement among desert climatologists. Imagine standing at the edge of the racetrack at dawn, frost cracking under your boots, watching a slab of ice the size of a kitchen table inch silently across the clay, dragging a dolomite boulder behind it. No engine, no hands. The trail it leaves will still be there in 10 years. The desert doesn't move things without reason. It just doesn't always tell you the reason. And the racetrack is only the beginning. The next anomaly doesn't hide in a remote playa. It sits in plain sight above a city of 4 million people. 12. Welcome to the invisible drought line. Lake Mead, the reservoir created by Hoover Dam on the Colorado River along the Nevada-Arizona border, is the largest reservoir in the United States by volume when full. It holds enough water to cover the entire state of Pennsylvania, 1 foot deep. In 2022, the waterline fell to its lowest recorded level since the reservoir first filled in the 1930s. The white bathtub ring on the canyon walls, calcium carbonate left behind as the water retreated, reached a width of 140 feet at its highest point. 140 feet of exposed rock that was underwater within living memory. Here is the anomaly. The Colorado River Basin receives its water from snowpack in the Rocky Mountains, accumulated over winter and released through spring melt. Standard hydrological models predict river flow based on snowpack measurements taken in January and April. For 23 of the 25 years between 2000 and 2024, actual river flow into Lake Mead came in below what those snowpack measurements predicted. Not occasionally, consistently, structurally. The gap has a name inside the hydrology community, the Colorado River Flow Deficit. But the mechanism behind it is still debated. One leading theory centers on what researchers call aridification, not just drought, but a permanent drying of the atmospheric column above the basin, which causes more snowmelt to evaporate before it ever reaches the river. The soil absorbs it, the air absorbs it. The river doesn't see it. According to research published by the Bureau of Reclamation, the basin lost approximately 1.5 trillion gallons of water to this atmospheric absorption effect between 2000 and 2021, water that the models assumed would flow downstream and didn't. The white bathtub ring at Lake Mead is not just a drought marker. It is a physical record of a miscalculation repeated for a quarter of a century. 40 million people in 7 states depend on that water. Somewhere in those 140 feet of exposed limestone is the line where the predictions stopped being right. No one has officially identified exactly where that line is, but the water is not coming back fast enough to cover it. 11. Welcome to the snow trap. The Cascade Mountains in Washington state run roughly north to south like a spine through the state's center, and on their western slope sits one of the wettest places in the contiguous United States. The Hoh Rainforest in Olympic National Park receives an average of 140 inches of rainfall per year. That number is well documented and well explained. Pacific moisture rolls off the ocean, hits the Olympic Peninsula, rises, cools, and falls as rain. Classic orographic lift. Textbook. But 40 miles to the east, on the far side of the same mountain range, lies a climate zone classified as semi-arid. Sequim, Washington, sits in what meteorologists call a rain shadow, a pocket of dry air created when Pacific moisture dumps itself on the western slopes and arrives on the eastern side, wrung out. Sequim receives approximately 17 inches of rain per year. The gap between 140 and 17 exists within 40 miles of road. The anomaly is not the rain shadow. Rain shadows are well understood. The anomaly is what has been happening to that rain shadow's edge since 2001. The transition zone, the geographic line where rainfall drops sharply, has been migrating. Climate monitoring stations operated by the University of Washington show the boundary has shifted approximately 8 miles eastward over the past 2 decades. What was semi-arid is getting wetter. What was already wet is getting wetter faster. The Hoh River, which drains the rainforest, now registers peak flow events in months that were historically dry. The models predicted the opposite. Warmer air over the Pacific was supposed to push the storm track north, reducing moisture delivery to the Olympic Peninsula. Instead, something in the atmospheric circulation is directing more storms southward and inland. The cause of that redirection is not agreed upon by atmospheric scientists at the University of Washington or at the National Oceanic and Atmospheric Administration's Pacific Northwest Research Station. One published theory involves changes in the jet stream's behavior related to reduced Arctic sea ice. Another involves decadal oscillations in Pacific Ocean temperature. Both have supporting data. Neither fully accounts for the pace of the shift. Somewhere on State Route 101, between the dripping moss of the rainforest and the dry lavender farms of Sequim, there is a line in the air that shouldn't be moving. It's moving anyway. 10. Welcome to the heat island nobody measured. Phoenix, Arizona is the 5th largest city in the United States by population, and it is the only major American city that has never recorded a temperature below 0 degrees Fahrenheit. That distinction is partly geography, the Sonoran Desert, and partly physics. Urban heat islands are real, well-documented, and expected in large cities. Concrete and asphalt absorb solar radiation and release it slowly through the night, keeping urban centers warmer than surrounding rural land. This is in every climate textbook. But Phoenix's urban heat island has become something the textbooks didn't anticipate in scale. A 2021 analysis by Arizona State University's Urban Climate Research Center found that since 1990, nighttime low temperatures in central Phoenix have increased at a rate approximately 3 times faster than daytime high temperatures. The nights are warming far more quickly than the days. In a standard urban heat island model, daytime and nighttime warming should track more closely together. The reason appears to be the sheer density of air conditioning units. Phoenix has one of the highest per capita rates of air conditioning use in the world. Those units pull heat from interior spaces and exhaust it directly into the outdoor air at ground level. At night, when the city's daytime solar absorption is at its peak release, the waste heat from millions of air conditioning compressors is simultaneously being injected into the same outdoor air that people breathe and sleep in. The cooling systems are, in effect, making nights hotter for everyone, while keeping individual homes cool. The practical consequence: Phoenix has recorded more consecutive days above 100 degrees Fahrenheit in recent summers than any other large city in American history. The summer of 2023 produced 54 consecutive days above 100 degrees, breaking the previous record of 45. The previous record had stood since 1974. The Municipal Heat Mortality Tracking System, a dashboard maintained by Maricopa County, logged over 600 heat-associated deaths in 2023. The number is large enough to require a separate category in the county medical examiner's records. What the models underestimated was not the desert sun, it was the feedback loop. The hotter it gets, the more air conditioning runs. The more air conditioning runs, the hotter the nights get. The hotter the nights get, the less the human body recovers. You don't need to live in Phoenix to recognize that loop. You just need to understand what happens when the thing keeping you alive starts making the problem worse. 9. Welcome to the frozen corridor. The Texas Panhandle town of Amarillo sits at an elevation of 3,607 feet on the southern edge of the Great Plains. It is not famous for severe winters. It is a city of roughly 200,000 people, with a regional economy built on cattle, agriculture, and energy production. In February 2021, Winter Storm Uri moved across the central United States, and temperatures in Amarillo dropped to minus 12 degrees Fahrenheit. That number alone is not anomalous for the northern plains. But Amarillo is not the northern plains. The anomaly is the air mass itself. Uri was driven by what meteorologists identified as a sudden stratospheric warming event, a disruption of the polar vortex, the circular wind pattern high in the atmosphere that normally contains Arctic air over the poles. The vortex buckled. Arctic air that should have stayed at high latitudes poured southward in a column that reached as far as the Texas-Mexico border. Laredo, Texas, which sits at the same latitude as Morocco, recorded temperatures below freezing for the first time in recorded history. The National Weather Service had no model that successfully predicted the depth and duration of the cold snap more than 72 hours in advance. A week before the storm, the official forecast for Central Texas showed temperatures below average, but well above freezing. The failure was not human error. It was a limitation of the modeling systems, which were not calibrated for polar vortex displacement events of this magnitude, reaching this far south. The infrastructure consequences are documented. Over 250 deaths attributed to the cold event across Texas, more than 4 million households without power at peak outage, and burst water pipes in structures that were simply never built to contain liquid water at minus 12 degrees. The pipes weren't built for it because, according to every historical climate record for the region, they didn't need to be. The stratospheric warming event that caused Uri has been linked by several atmospheric research groups to changes in Arctic sea ice concentration. Thinner ice over the Barents Sea in autumn appears to create thermal instability that makes polar vortex disruption more likely. That link is described as probable in peer-reviewed literature. It is not described as certain. The distinction matters. If it's certain, it's a projection. If it's probable, it's still a warning. Uri left a water stain on the ceiling of a Walmart in Amarillo that you can still see from the inside, if you know where to look. 8. Welcome to the Singing Hole. Turkalo. No. Let's go somewhere real and specific. The door to the underworld is what locals in the Barrow, Alaska region, now officially called Utqiagvik, began calling the thaw slumps appearing along the Arctic coast of northern Alaska. A thaw slump is a landslide caused by melting permafrost. When the ice inside frozen ground melts, the soil loses its structural integrity and collapses. The slumps along the Beaufort Sea coastline near Utqiagvik have been cataloged by the United States Geological Survey since the 1950s. Between 1955 and 1979, the average annual coastal erosion rate was 6 feet per year. By 2020, that rate had reached 35 feet per year in the most active zones. 35 feet per year means that in some stretches, a line drawn on the sand in January is 35 feet out over open ocean water by December. Structures built on permafrost, including fuel storage tanks, water treatment infrastructure, and residential buildings, are being consumed by the retreating coastline on a timeline faster than the municipal budget for relocation can accommodate. But here is the piece that doesn't appear in the standard erosion reports. Inside the thaw slumps, as the permafrost collapses, and organic material that has been frozen for 10,000 years suddenly thaws and begins to decompose. The ground releases methane, not in a controlled or measurable plume, in irregular, unpredictable bursts. Field researchers from the University of Alaska Fairbanks have documented methane concentrations inside active slump zones that are 4 to 6 times higher than the ambient Arctic air. Methane is a greenhouse gas, approximately 80 times more potent than carbon dioxide over a 20-year period. The feedback loop implied by that number is significant. Warming melts permafrost. Permafrost releases methane. Methane accelerates warming. Warming melts more permafrost. Climate models have included permafrost feedback in projections for years. The anomaly is the rate. The erosion accelerating from 6 feet to 35 feet per year represents a factor of nearly 6 times. The models projected a factor of roughly 2 to 3 by mid-century. The rate arrived at mid-century pace 30 years early. The ground beneath Utqiagvik is not just thawing, it is leaving. 7. Welcome to the Ghost Rain. The Great Plains of the United States, that broad inland sea of grass stretching from Nebraska south through Kansas, Oklahoma, and into northern Texas, depend on a weather pattern called the low-level jet. It is an atmospheric river of fast-moving air that flows northward from the Gulf of Mexico at low altitude, typically at night, and delivers moisture to the semi-arid plains. It is the reason the Ogallala Aquifer, the largest underground freshwater system in North America, originally filled over thousands of years of rainfall. Without the low-level jet, the Central Plains would be closer to desert than farmland. Since 2012, the low-level jet has been weakening. Not consistently, not linearly, but on average, the jet is delivering less moisture to the Central Plains than it did for the previous century of instrumental records. A 2022 analysis published in the journal Nature Climate Change found that the jet's average nighttime peak wind speed has dropped by approximately 12% since 1990. 12% sounds modest. It is not. The Great Plains receive a disproportionate share of their annual rainfall from nocturnal thunderstorms fed by the low-level jet. A 12% reduction in moisture delivery translates to a significantly larger reduction in the frequency and intensity of those storms. The Ogallala Aquifer is being pumped at 8 times the rate of natural recharge. That number is well publicized. What is less discussed is that the recharge rate itself is also declining as the low-level jet weakens. The depletion is coming from both directions at once. More water pumped out, less water falling in. Towns in western Kansas that have relied on Ogallala water for generations are already making decisions about which fields to retire. Garden City, Kansas, a regional agricultural hub, convened a water planning meeting in 2023 in which, for the first time, local officials formally discussed the scenario in which the aquifer in their district is non-viable within 40 years. The jet stream is quieter than it used to be. The fields are not. 6. Welcome to the lake that shouldn't be. The Salton Sea in Southern California is the largest lake in the state by surface area, roughly 343 square miles. It was created by accident. In 1905, an irrigation canal feeding agricultural land in the Imperial Valley broke under pressure, and the entire flow of the Colorado River poured unchecked into the Salton Sink, a below-sea-level desert basin, for the next 2 years before engineers could stop it. The result was a lake in the middle of the desert that had no natural water source and no natural outlet. The Salton Sea has been evaporating and concentrating salt ever since. Its current salinity is approximately 50 parts per thousand, significantly saltier than the Pacific Ocean at 35 parts per thousand, and getting saltier each year as fresh water evaporates, but the salts remain. The fish population, which once supported a thriving sport fishery in the 1950s and 1960s, collapsed as salinity exceeded the tolerance of tilapia, the last surviving fish species, in the late 2000s and 10s. But the anomaly is not the salinity. The anomaly is what the retreating shoreline releases into the air. The lakebed that is now exposed, approximately 100 square miles of former lake bottom as of 2024, is a fine, powdery sediment containing high concentrations of selenium, arsenic, and pesticide residues accumulated over a century of agricultural runoff from the surrounding farmland. When the wind blows across that exposed lakebed, which sits at the bottom of a natural wind funnel between two mountain ranges, it picks up that sediment and carries it north and east into the Coachella Valley and the Inland Empire, where more than 4 million people live. Asthma hospitalization rates in communities downwind of the Salton Sea, particularly in the eastern Coachella Valley, are among the highest in California. The state agency tracking this is the California Air Resources Board. Their data connects elevated particulate matter events directly to wind events over the exposed lakebed. The connection is documented. The solution, restoring water to the lake to keep the sediment wet, requires an estimated $200 million in infrastructure and a water source that is itself under allocation pressure from the Colorado River crisis. The Salton Sea is a lake with no future and a shoreline that functions as a slow-moving hazard. From the road above it on a clear morning, it looks like something out of a dream. Blue water, mountain backdrop, pink-orange light on the surface. Beautiful, in the way that things sometimes are when they are ending. And what comes next makes the Salton Sea look straightforward. Brace yourself. 5. Welcome to the forest that moved. The boreal forest, the vast belt of spruce, fir, and pine that covers the interior of Alaska and northern Canada, is one of the largest terrestrial ecosystems on Earth. It is also moving, not through dispersal of seeds over generations, in the way forests normally migrate across centuries. It is moving fast enough that researchers at the University of Alaska Fairbanks can measure it in real time using satellite imagery analyzed year over year. The tree line, the boundary beyond which trees cannot survive, has historically sat at approximately 67 to 68 degrees north latitude in interior Alaska. Over the past 3 decades, trees have been establishing themselves at 69 and in some locations 70 degrees north. At the same time, the southern boundary of the boreal zone is retreating southward in some areas, as warming causes stress and die-off in mature forest stands. The forest is not simply moving north, it is thinning in the middle. The anomaly within the anomaly is fire. Alaska's wildfire season now regularly extends into months, late April, early May, late October, when burning was historically rare because ground moisture and temperature did not support it. The 2022 Alaska fire season burned approximately 3 million acres, with fires igniting on dates and in locations that the Alaska Division of Forestry's historical fire models did not flag as high risk. One fire, the Lime Complex near the Yukon River, burned through permafrost terrain that had not experienced significant fire in more than 500 years, based on soil carbon dating. When permafrost terrain burns, the black carbon deposited on the soil surface absorbs sunlight that was previously reflected by the white ground cover. It accelerates permafrost thaw. The thaw releases methane. The methane warms the atmosphere. The warmer atmosphere creates conditions for more fires. The cycle has a name in the scientific literature, a positive feedback spiral. The naming of it is the easy part. The stopping of it is not yet on any timeline. The forest is moving, and it's leaving fire behind it. 4. Welcome to the Dead Zone's pulse. At the point where the Mississippi River empties into the Gulf of Mexico, roughly 60 miles south of New Orleans, near the town of Port Fourchon, Louisiana, the water changes color. Green gives way to a murky, brownish green, gives way, in summer, to a vast expanse of ocean where very little lives. This is the Gulf of Mexico Dead Zone, an area of severely oxygen-depleted water that forms every spring and summer, and has been measured continuously since 1985. The dead zone is caused by nutrient runoff, primarily nitrogen and phosphorus from agricultural fertilizer, applied to crops in the Mississippi River watershed, which stretches from Montana to New York and covers approximately 40% of the contiguous United States. That runoff feeds enormous blooms of algae in the Gulf, The algae die and sink. Bacteria decompose them on the seafoam floor. The decomposition consumes oxygen. The oxygen drops below the level that fish, shrimp, and crabs can survive. They either flee or die. Trawling boats working the edges of the dead zone find it by the absence of their catch. The anomaly is the size. When the dead zone was first systematically measured in the early 1980s, scientists projected that reducing Mississippi River nitrogen loads by 30% would significantly shrink the zone. The United States Department of Agriculture and the Environmental Protection Agency together launched a nutrient reduction framework in 2008 with the target of reducing the dead zone to less than 2,000 square miles by 2015. In 2015, the dead zone measured 6,474 square miles. In 2017, it measured 8,776 square miles, the largest ever recorded, roughly the size of New Jersey. In 2023, the measurement was approximately 3,058 square miles, one of the smaller years in the record. The variance from year to year is enormous. Small years happen when late-season winds mix the oxygen back into the water. Large years happen when spring flooding sends record nutrient pulses down the Mississippi. The projection of linear reduction from conservation measures has not materialized. Farmers have adopted some nutrient management practices. The nitrogen entering the river has not decreased proportionally. The soil carbon stores, the biological sponge that should absorb excess nitrogen before it reaches the water, have been depleted over a century of industrial farming, to a degree that restoration programs have not been able to offset. Every summer, the fishing boats that work the Louisiana coastal shelf move east or west to find the edge of the dead zone. The edge is always somewhere. It's just never quite where the models said it would be. Now we enter the final three. The scale changes. 3. Welcome to the storm engine, Hurricane Alley, the stretch of the Gulf of Mexico and Caribbean that feeds the Atlantic hurricane season, has been producing storms differently than it did 40 years ago, not more frequently by raw count. The total number of named storms per decade has not increased dramatically. What has changed is intensity. The proportion of storms that reach Category 4 or Category 5 strength has increased significantly, and the speed at which storms intensify has changed in a way that no seasonal forecast model predicted. Rapid intensification is the term used when a hurricane strengthens by 33 miles per hour or more within 24 hours. It is the nightmare scenario for emergency managers because it compresses the warning window. A storm that is a Category 1 on Monday morning is a Category 4 by Tuesday morning, and the evacuation order that might have been issued 72 hours in advance is now issued with 24 hours to act. Hurricane Ida made landfall in Port Fourchon, Louisiana, on August 29, 2021, the exact anniversary of Hurricane Katrina in 2005. In the 18 hours before landfall, Ida intensified from a Category 2 storm with winds of 100 miles per hour to a Category 4 storm with winds of 150 miles per hour. That rate of intensification is now documented in case studies at the National Hurricane Center. The anomaly is the water. The Gulf of Mexico in 2021 had areas of warm water extending to a depth of more than 300 feet below the surface. Standard hurricane intensification models assume that as a storm passes over the ocean, its churning mixes cooler deep water up to the surface, which slows the storm's intensification. That mechanism depends on cool water being available within 150 to 200 feet below the surface. In 2021, over significant portions of Ida's track, it wasn't. The storm drew on warm water far deeper than historical averages, and the braking mechanism didn't fully engage. The term for the warm water layer is the hurricane heat content anomaly. It is measured by satellite and buoy, and the values recorded in the Gulf of Mexico in 2021 and again in 2023 were, in several locations, the highest in the satellite record going back to 1993. One researcher from the University of Miami, speaking at a 2022 conference on Atlantic hurricane activity, described the 2021 Gulf heat content as, in her words, unprecedented. Unprecedented in the satellite record, which means unprecedented in any record we have the instruments to measure. Port Fourchon sits so close to the water's edge that the road into town floods during high tide events that would not have flooded it 30 years ago. The road is still there. The town is still working. The rigs and pipelines and logistics that make it one of the most important ports in the Gulf of Mexico are still operational. But the water is closer than it used to be, and what's underneath the water is warmer than it has ever been measured. 2. Welcome to the record that broke the record. In the summer of 2021, the Pacific Northwest of the United States experienced what atmospheric scientists have since called a once-in-10,000-year heat event. The term comes from statistical analysis of historical temperature distributions, an event so far outside normal variance that, under pre-2021 climate conditions, it should have occurred with a frequency of approximately once in 10,000 years. On June 28, 2021, the town of Lytton, British Columbia, just north of the Washington state border, recorded a temperature of 121 degrees Fahrenheit. The all-time temperature record for Canada was broken 3 days in a row. Portland, Oregon, hit 116 degrees. Seattle hit 108 degrees. Seattle had never in its recorded history exceeded 100 degrees before June 26, 2021. It exceeded 100 degrees 3 days in a row. The event was driven by a heat dome, a high-pressure system that settled over the Pacific Northwest and trapped hot air against the surface like a lid on a pot. Heat domes occur. They are in the climate record. What made this one unprecedented was its combination of intensity, duration, and geographic scope. Climate attribution scientists from the World Weather Attribution Initiative published an analysis within weeks of the event, concluding that it would have been virtually impossible without human-caused climate change, meaning the underlying atmospheric conditions that allowed the heat dome to reach those temperatures would not have existed in a pre-industrial climate. More than 600 deaths were attributed to the heat in Oregon and Washington in the 2 weeks following the event. In British Columbia, the coroner's office attributed more than 600 additional deaths to the heat. The total is the deadliest weather event in Pacific Northwest recorded history. The anomaly within the anomaly. The modeling community was caught off guard. The ensemble models, the battery of simultaneous simulations run by national weather agencies, did not project temperatures in that range, not even close. The highest projections fell short of actual temperatures by 10 to 12 degrees Fahrenheit. After the event, climate scientists conducted what is called a post-event attribution analysis. Their conclusion was that the event fell outside the envelope of what their models were calibrated to simulate. The statistical framework they used assumed that extreme heat events would cluster around the high end of historical observations, with some additional warming offset. The 2021 heat dome was not an extension of historical observations. It was a departure from them. There is a word for data that falls outside the model envelope. The word is outlier. The question that no official report has fully answered is whether an event this far outside the model envelope is truly a statistical outlier, a rare extreme, or whether it is evidence that the models themselves are not capturing the full range of what the climate system is now capable of producing. That question is still open. The temperature record in Lytton is not. And now, the one place where the anomaly has a number that no instrument in human history had measured before. 1. Welcome to the water that should not exist. In the summer of 2023, the sea surface temperature of the North Atlantic Ocean broke every record in the instrumental record. Not by a small margin, by a margin that stunned the scientific community. Sea surface temperatures in the North Atlantic in July and August 2023 were on average 1.1 degrees Celsius above the previous record for the same period, which was itself set just 4 years earlier in 2019. 1.1 degrees Celsius above a record. That number requires translation. In the language of ocean heat physics, 1 degree Celsius across the surface of the North Atlantic represents an enormous quantity of thermal energy, equivalent, according to estimates published by the National Oceanic and Atmospheric Administration, to trillions of kilowatt-hours of heat absorbed into the water. The ocean has enormous thermal mass. Moving its average temperature by 1 degree takes an extraordinary amount of energy input, sustained over time. Moving it by more than 1 degree above the previous record, in a single year, means something in the energy balance changed significantly and recently. But the Atlantic was not alone. In the Gulf of Mexico, buoys maintained by the National Data Buoy Center recorded sea surface temperatures in July 2023 that exceeded 100 degrees Fahrenheit in the shallow waters off the Florida Keys. 101.1 degrees Fahrenheit was measured at a buoy near Manatee Bay on July 24, 2023. That reading, if confirmed by peer review, the data was still under formal review as of the most recent published analysis, would represent the highest sea surface temperature ever recorded by an in-water instrument anywhere on Earth. 101 degrees. In the ocean, water that warm is lethal to most forms of coral and severely stressful to any marine organism that cannot swim away from it. The coral reef system along the Florida Keys, already badly bleached by previous warming events, experienced near-total bleaching across entire sections of its shallow water habitat in the weeks following that temperature peak. Bleaching is what happens when corals expel the symbiotic algae living in their tissue because the water is too hot. Without those algae, the coral is white, starving, and within weeks, dead. The anomaly is not that it happened. Coral bleaching has been documented since the 1980s. The anomaly is the speed. The rate at which sea surface temperatures globally crossed from record high into uncharted territory in 2023 was faster than any climate model had projected for that year. The models anticipated record years. They did not anticipate those specific temperatures at that specific time. Climate scientists at the University of Reading in the United Kingdom published a paper in late 2023 stating that the North Atlantic temperature anomaly of 2023 exceeded the upper bound of their model simulations. Not the high end, the upper bound, which means the models did not contain a scenario in which this outcome occurred. The measured reality fell outside the space that the models had defined as possible. There are several candidate explanations. The 2022 eruption of the Hunga Tonga volcano in the Pacific injected an unprecedented volume of water vapor directly into the stratosphere, and water vapor is a potent greenhouse agent. The phasing out of sulfur-rich shipping fuel under new international maritime regulations in 2020 reduced the aerosol layer over the oceans that had been partially reflecting sunlight, essentially removing a cooling effect that had been masking some of the underlying warming. The ongoing buildup of greenhouse gases in the atmosphere provided the baseline energy input. The combination of all three in a single year may have produced an effect larger than any one factor would suggest. That is the leading composite hypothesis. It is published, it is peer-reviewed. It is also, in the words of one of its authors, a best current explanation, not a confirmed mechanism. Imagine standing on the edge of a dock in the Florida Keys in July 2023, reaching your hand into the water. The water feels like the inside of a car left in summer sun for 2 hours. And below your hand, stretching away into the distance, 40 feet down, 20 feet down, 10 feet down, is what used to be one of the most biodiverse marine ecosystems in the Western Hemisphere. White, silent, still. The sea surface temperature in the North Atlantic returned to closer to normal levels by late 2023 and into 2024. The coral does not recover on that timeline. Coral reefs grow at roughly 2 to 3 centimeters per year in optimal conditions. What was bleached in weeks requires decades to restore. If the water stays within survivable range, if it does not happen again before recovery is possible. The ocean set a record in 2023 that no instrument had ever recorded. The record stands in a database at the National Oceanic and Atmospheric Administration. The database keeps updating. The record may not stand much longer. Not because conditions improved, but because the numbers keep moving. 13 places, 13 sets of numbers that don't quite match the projections. Rocks that move without wind enough to move them. A reservoir ring marking 2 decades of missed predictions. A rain shadow boundary shifting against the forecast. A city hotter at midnight than the models said it would be. An Arctic coast retreating at 6 times the projected rate. An underground aquifer losing its rain at the same time it loses its water. A lake releasing its poison floor into the wind. A forest on fire in places it hasn't burned in 5 centuries. A dead zone that ignores its own reduction targets. A hurricane that intensified through water that shouldn't have been warm enough to feed it. A heat dome that fell outside the edges of the model. And an ocean that ran a temperature no instrument in human history had ever measured. None of these are individually secret. The data is public. The papers are published. The sensors are running right now, updating their readings into government databases that anyone can access. What isn't simple is the pattern. 13 anomalies in 13 different systems, using 13 different physical mechanisms, all moving in the same direction, at rates faster than the projections. So here's the question this video leaves with you. 2 of the entries you just heard involve things you directly depend on. Water in the Colorado River system, or air in the Gulf states. Which one worries you more? The reservoir ring showing 40 million people's water supply running below projections for 23 years? Or the ocean temperature record that broke the upper bound of what the models said was possible? If this made you think differently about the numbers behind the forecast, the like button is right there. That one click tells the algorithm this kind of investigation belongs in more feeds. Stay safe and see you soon.